So this question is from CSIR 2020 paper, June 2020. So the 22 question number says that if fn be a bounded function, then which of the following statement is not true? So four options are given. So if we consider this, suppose let fn equal to 2, then limit n tends to infinity, supremum of fn will be 2, which belong to this set of natural numbers. Okay. Similarly, if limit n tends to infinity, infimum of fn will be 2, which is also this natural number. Now if we consider the option 3, so limit n tends to infinity, infimum of fn plus n, that is 2 plus n, it will be infimum of 2 plus n, which is minus infinity, and it does not belongs to the set of natural numbers. And consider the option number 4, limit n tends to infinity, the sub of fn plus n, right? So it will be written as limit n tends to infinity, supremum of 2 plus n, which is not bounded above, so it is infinity, and it doesn't belongs to this set of natural numbers. So in this question 22, our option 3 is not correct. Question 23, which of the following statement is true? So let's check one by one. So option 1, it is saying that there are at most countably many continuous maps from R2 to R. Okay, so consider is f of x plus y, or you can write it f of xy. It's two functions, is written as x plus a. For each a belongs to this set of real numbers, right? Since fx, this is continuous, there will be infinitely many continuous maps. So here it is say that countably, so since f of xy is continuous, so there will be infinitely many continuous maps from R2 to R. So there are infinitely many continuous maps from R2 to R. So in our case, the option 1 is incorrect. So option 2, there are at most finitely many continuous surjective maps from R2 to R. So if we consider the same example, this f of x is x plus a, f of xy is x plus a, right, such that f of xy is x plus a, such that for each a belongs to this real space R. So f of xy, we know that it is continuous surjective map. Okay, and there will be infinitely many continuous surjective maps from R2 to R, right? Infinitely continuous surjective maps from R2 to R. So option 2 is correct. Okay, now check with the option 3. So there are infinitely many continuous injective maps from R2 to R. So now if we consider that if f, which is mapping from R2 to R, is continuous, it is continuous, and since R2 is connected, right, since R2 is connected, its image under f is connected. Okay, its image under f will also be is connected, right? But if you remove any point from this R2 space, it will remain connected, right? If we remove any point from it, it will remain connected. But if we want to remove a point whose image is in the interior of the interval, then the image cannot be still connected if the function is injective. So for injective function, we cannot say that it is connected, right? So there is no such map, and there will be no continuous injective maps, no continuous injective maps from R2 to R. So that's why our option 3, it will be incorrect. And what is the option 4? So there are no continuous bijective maps from R2 to R, and that is you can quite straightforward from the 3. So because we already proved that there are no continuous injective maps from R2 to R, right, in option 3, so there will be no continuous bijective maps from R2 to R. So this option 4 is also correct. So we have to find which of the options are correct. It's true. So in our case, there are no continuous bijective maps from R2 to R. So this will be the correct solution.